open this computer. I want to show you and share with you my Canvas screen, which is right there. And I want to talk about what we're going to do in lab tomorrow. Hopefully you'll see Canvas. There it is coming up. Yep. And if you look, this is the home page for our course, and the lectures that I've given last week, 23rd, 25th, 27th, are right there. And then right below it is the lab for this week, which we'll be doing tomorrow, or you can do tomorrow. It's an asynchronous lab. That means you can do it whenever you want. What I did over the weekend is I prepared 5 fairly short videos. I think the longest one is about 6 minutes. In total, the total videos are about 30 minutes. And that would be the data you would have been taking if we were meeting in Dunning Hall in the class, in the lab, and doing this in real time. The lab handout turned out I just modified it a little bit. So you watch me do the experiment. I'll show you the indications on Logger Pro or on a multimeter, and you log those, and then you do the calculations, and you see if what we're measuring on the videos is what you predict. If you look at the lab handout, it's about 6 pages. The first 2 pages are theory. You don't have to fill anything in on them. I would recommend that you just print out those 5 pages and answer the questions one at a time, turn it in. It's obviously an individual report. There's no executive summary. Just answer the questions, do the calculations, and that's what it says at the end. And just to give you, these are all on my YouTube channel. If for some reason Canvas doesn't work well for us, but you can see here's the first video coming up. It looks YouTube-like because that's where it's coming from. That's actually an old computer modem that I had that I ripped apart. I took 2 of the capacitors out of it. And you can see here's my basement where we're going to do the experiment. There's the multimeter that you'll see the data on. It might not surprise you. You're going to put, for the first part, part A, you're going to put the capacitors both in series and parallel and take some data on it and then do some predictions of what they should be. Okay. And it's pretty self-explanatory. If you have any trouble with the videos, or if you can't figure something out, I don't have an office hours planned tomorrow, but if you need to, I'll certainly set that up. So let me know. Okay, any questions on the lab? You got to have it done. If you look back, let me close this out. Assignments, and I think you got to keep an eye on assignments because that's how I communicate due dates to you. Okay, and I think the next homework is due Wednesday, I guess, at midnight. Wednesday night. That'll be the chapter 28, the Kirchhoff's rules, the circuits, and that's what, of course, this lab is all about. So I would probably think it'd be helpful to do the lab before you try to do the homework. If that's an issue, I can always move the homework to a later date. Pay attention to the worksheets. Let's see, there's a worksheet due today, I guess. Today's worksheet due at the end of business hours today is worksheet 23 on what we talked about on Friday. RC circuits, a resistor and a capacitor in the same circuit. That's due end of the day today. I will have normal office hours this afternoon, except I'm going to slide it a half hour. Normally I go 12:30 to 1:30 when we're in person back in Dunning Hall. It takes me a little bit of time to make the video from my last class and convert it, put it up onto YouTube for them. And so I just want to give myself a half hour. So office hours will start at 1, go nominally till 2 if you got any questions on worksheet 23. Something else I want to share with you, and it's just a resource one of my quantum mechanics students showed me. So I'll stop sharing this. And let's see, we'll share my iPhone, iPad, and screen mirroring. Yes, yes, yes. And this is it's called AWW app. It's awebwhiteboardapp.com. And you saw I was using a pretty rudimentary whiteboard to be writing in class. And this one's a little bit better because I can make things smaller. I can shrink them, and then I can push them up into the side. The other thing it has that's handy is it's got this collaborate button. I offer this to you as a resource because it's dawned on me that if you have a pen like one of these with the rubber tips, throwing it around, one of these guys, and you have some sort of tablet you can write on, a lot of you are not printing out things, and that's fine. You just, if you're writing it out on a piece of paper though, then you have to photograph it and upload it. If you're using a whiteboard app like this guy, you can see you can just save it there's an export the board, and it just basically saves it. And I assume a PDF. I haven't tried it. It could be a JPEG. I don't care. But that saves you a step because you just do your work on this tablet if you have a device like this, and then you can just save the file and immediately upload it. Save you the step of having to photograph it. So I just kind of throw that out to you. It's helpful, and that's it. That's all I got. Let's talk about the class today. And so I'll stop sharing this. New material you should have noticed. We're talking about magnetism now. We're done now. We're still going to make circuits with currents that make magnetic fields. That's coming. So it hasn't gone away. But in the short term, I guess, we're done doing Kirchhoff's loop equations. Instead, we're in chapter 29 now, and we're going to be talking about magnetic fields. And so this screen should come up for you in just a second. Yep, there it is. Let's put these guys away so that it doesn't interfere with our video. And of course, we're talking about magnetism, and most people's experience with magnetism is with ferromagnetism. Ferromagnetism is those permanent magnets that we all like to play with. It could be on your kitchen refrigerator, but you've all done it. You've had two, and you found if you pointed one end against another end, and the ends were the same pole, North Pole or South Pole, or the names we give to them, if they were both the same, the magnets repelled each other. On the other hand, and that's the same with the two South Poles, on the other hand, if you flip the thing around and you have a North Pole and a South Pole, they're attractive. And of course, the rule is similar to charges, where we said like charges repelled, either two positives or two negatives. We've renamed positive and negative to north and south. And of course, unlike, like negative and positive charges attract, the North and the South Pole attract. Okay, and there's a significant difference, though, between electric charges and magnetic poles. And it comes down to this question: what would happen if you broke the magnet? Maybe you took a saw and you cut this thing right in half right here. And then I guess the same thing on a set of electric charges if you cut right here. And the answer is, in the electric case, you can take the positive charge, move it away, the negative charge stays by itself, and you can have a point charge. If you try to, point positive or negative, if you try to do the same thing with the magnet, you cut it right here, what you'll find is you develop a South Pole right here and a North Pole right here, and these field lines kind of curve around like this then, and then these ones over here kind of curve around like that. So if you cut a dipole, a magnetic dipole, in two pieces, what you make is two more dipoles. On the other hand, if you take an electric dipole and you cut it into pieces, what you create is a single charge. We refer to that as a monopole, one pole. You can do that with electric charges. You cannot create a magnetic monopole by separating it out. Now, I should tell you, before the end of your lifetime, that fact that I just stated right there, that there is no such thing as a isolated North or an isolated South Pole, may be proven false. There are a number of people researching, exactly looking for that thing in nature, that individual North Pole without a companion South Pole, or a South Pole without a companion North Pole. Active area of research today. To date, nobody's found it. We accept in science that there is no such thing as a North Pole isolated, a monopole, or a South Pole isolated. But who knows? Could happen in our lifetime, maybe your lifetime. I doubt it'll be found in mine. In any event, a couple of things that you should have noticed as well different is when I drew let's go back one. When I drew the poles, the electric field lines, that's the kind of orangish red line here, it starts on a positive charge, the electric field line does, and it ends on a negative charge. That's why you're able to just pull a positive or a negative charge away, because its field lines start or stop there. In the case of a magnetic field, this picture down here in the lower left corner, it's actually the best picture, because you can see inside the magnet, the field lines continue. Now they're drawn dashed here in this particular diagram, but they start on the north side, come around, and they make complete loops. That's fundamentally why there's no such thing as a magnetic North Pole that's isolable, a monopole by itself, because the magnetic field lines continue around in closed loops, whereas in the electric field case, they actually start electric field lines start at one charge and end on another. Fundamental difference. Again, somebody may do research and find exceptions to that, but every case we know of magnetic field lines today, the lines are continuous. Okay. And so you see drawings like this one up here, a little bit misleading because they don't draw the field line inside the magnet, and that's a problem. All right, a couple of things that we should recognize, and I'm putting together big picture stuff that we've talked about through the course of the semester, because we started off talking about gravity and gravitational fields, and I think hopefully you recognize that gravitational fields are caused by masses. Big ones like the sun or the earth or the moon, and even little ones like an object that sits on a table creates a gravitational field. It's just very weak. Okay. And if you need to find the force due to a gravitational field, you get the gravitational field from how much mass there is, like on the earth, and then you multiply it by the mass that's being influenced by that gravitational field, and you can figure out the force of gravity, something we call weight. We did a little later on in the semester exactly the same thing with electric fields. Electric fields, we said, were caused by charges. Okay, and so a charge causes an electric field, and then if you bring another charge in the vicinity of that charge which created the electric field, a force acts on it, given by this equation. And so then the question, of course, is these magnetic fields that we're starting to talk about today, what causes them? And the answer is a moving charge. And so if I was looking, and we're going to be talking about the sources of magnetic fields all this week, Monday, Wednesday, Friday of this week, and the math gets a little bit more intense than it did for either the gravitational or the electric field case. And so that's why we're going to spend a couple days on it. And then next week, we're going to talk about, all right, well, what is the relationship between the charge moving at some speed and the field, which causes a magnetic force? And that little f here just means it's got to be a function of how much charge there is, how fast the charge is moving, and how strong the magnetic field is. Okay, and so we're going to study that next week, and we'll spend about 3 days on that as well. Okay, and so that's kind of the outline of things, and hopefully you've seen some a kind of a big picture pattern in physics from this semester. I will say this, and I didn't assign it. If you think about it, what's the difference between an electric field, which is caused by a charge, and a magnetic field, which is caused by a moving charge? And if you think about that, it really does boil down to just being the frame of reference. Okay. If the charge is moving relative to your frame of reference, well, then you call it a magnetic field. But if the charge is stationary relative to your frame of reference, you call it an electric field. But what if you're moving with the charge? If you're moving with the charge, then what one person might call a magnetic field, in your frame of reference, you might call it an electric field, because in your frame of reference, the charge is stationary. That's a little bit bizarre, and that's the kind of stuff that Einstein figured out at the beginning of the 1900s with his relativity work. And it wasn't Einstein who realized, but it was quickly determined that electric and magnetic fields really are different ways of looking at the same phenomenon in nature. But for an introductory course, we're going to treat them separately. Okay. And the math, of course, is significantly different for the two. All right. A little bit about navigation. A lot of you know I was in the Navy. Before this, I was actually a navigation officer on one of my submarines, USS Alexandria. And we didn't use compasses to navigate very much. But of course, that was done. And those of you that do hiking and orienteering, that sort of thing, I'm sure you probably use a GPS these days, but a little bit of magnetic compass work. And if everything I've said is true, one of the things you have to realize is that needle on a compass has to be a little magnet, doesn't it? Very small, lightweight one. And what it does is it gets attracted towards the Earth's geographic North Pole to point towards north. On the other hand, the south pole of that needle gets attracted towards the geographic South Pole. That gives us an interesting conclusion here, I guess. And that means if there is an attraction between the compass needle and the geographic North Pole, then the geographic North Pole of the Earth must magnetically be a South Pole, and the geographic South Pole of the Earth must magnetically be what we call a North Pole. Now, remember, these names are completely arbitrary, right? Man-made. we decided that the direction that the compass needle pointed was north, and somebody decided that that's what we were going to call that pole of a bar magnet. But that does leave you with the conclusion that what's at the geographic North Pole is actually magnetically a South Pole. And that's what happened as the Earth cooled. Okay. Now, a couple things. The first is this idea of magnetic declination. If you're ever out sailing or something or hiking and you're using a magnetic compass, you should recognize that the axis of rotation of the Earth will establish a north-south pole axis. The magnetic pole, that magnetic south pole, is not concurrent with the axis about which the Earth rotates. They don't sit on the same geographic location. That's called declination. And in fact, if you really look into it, you'll see the magnetic pole is a little bit below the ground, and further it migrates, it moves as the Earth goes through its cycles around the sun and rotates. It varies, and so we do geographic and geological surveys to figure out exactly where the magnetic North Pole is relative to the axis on which the Earth is spinning up at the North Pole, because they're different and they move around. Another thing you'll see is while at the equator, the magnetic field is pretty much perpendicular. I'm sorry, the magnetic field is parallel to the surface of the Earth, perpendicular to the normal to the Earth. As you move into higher latitudes, they're like right here, if you look, the magnetic field is not parallel to the Earth's surface. It's actually down a little bit from horizontal, pointing a little bit towards the ground, maybe only a few degrees. That's called angle of dip. So there's actually a vertical component to the magnetic field in the downward direction. It's not pointing straight north. Probably where we are, it's straight north and a little bit down. And so that's true in the southern hemisphere. Obviously, it would be pointing straight north, but a little bit up relative to the tangent to the surface. They're just not quite parallel. And that's truth because of the way the field lines have to be, and the fact that, as I pointed out, the South Pole at the Earth's geographic North Pole isn't at the surface. It's a little bit below the ground. Some stuff on navigation, just some general Earth science. If you go on to take Professor Kem's classes, you'll talk more about it, but just a little bit of a primer on that kind of stuff. Now, there's another type of magnetism, which you may think about as being completely different from what I've described here so far. Because when I'm talking about the Earth and pieces of metal that we magnetize, by the way, that's called ferromagnetism. There's actually 3 naturally occurring magnetic materials in nature, and that's iron, cobalt, and nickel. Those are the only 3 that are naturally magnetized as elements. There's another way, though, to create a magnetic field, and we said moving currents are the source of magnetic fields. Think about a second, what's moving in a cobalt, iron, or nickel element that could be moving to cause a magnetic field? And you quickly realize that, well, the charged parts of the element, the atom, either the rotation, the orbit, kind of the swirling of the electrons around the nucleus, that could be a source of a magnetic field. The spinning of individual electrons, that would be moving charge. And if those all lined up, you could potentially get magnetism, and you do. That's exactly the nature of the naturally occurring magnetic fields in ferromagnetic materials. But we can force charges to move, and that's what we did in the previous chapter when we connected batteries to wires and ran it through resistors. We can actually force charges to move through wires, and moving charges in wires, currents, do in fact create magnetic fields, and that's how we can harness that device. And so this was work done by a guy named Oersted in the early 1800s, and he's just envisioning maybe a current carrying conductor right here, a wire that he's hooked a battery to, so that the current is perhaps moving in the upward direction. And what he quickly saw is that the filings here created little circles going around the wire. Now, I didn't notice it. I'm sure you've all seen it. When we looked at the dipole of the ferromagnetic materials, you can see the same sort of thing happening. The magnetic fields are lining up the little pieces of iron that are suspended here, these metal filings, and tracing out the same magnetic field lines that we're talking about. What Oersted figured out is when you have a current there is some magnetic fields that are swirling around. The problem with the iron filings that are suspended here, you got no idea which way the magnetic field is going. I kind of presumed that way. It turns out I drew it wrong. Okay, and we'll talk about that. Oersted figures out it's actually going the other direction. If the current is going up, the magnetic field is swirling around in a counterclockwise direction in this particular diagram here. And the way Oersted figured this out, it might not surprise you, is he did a little experiment like this, where there's my current going upward in the wire, and he put a bunch of magnets going around, and you can see the red side here is the north side, and they all lined up in a circle all the way around here. And so that's how he determined that if the current is going up, the magnetic filings, the iron filings here, told him it was swirling around. So he put some compasses in, and now we actually know what direction those are going. All right, there's a notation now you've got to kind of get a handle on, because you can see right away that magnetism is a three-dimensional phenomenon. When we had two charges, you were pretty good just working on a piece of paper, right? Because these two charges would attract each other in the plane of the paper, right? No problem. We didn't need a third dimension. We didn't need into or out of the page. But if you look now, the thing that's creating the current might be in the Z direction, and the magnetic field might be in the X and the Y direction in a little circular path going around. So we need a convention to show both into and out of the page as a very minimum. I mean, we might need to do better than that. But in this course, things will tend to happen either perpendicular to the page, into or out of the page, and then into the page at in the plane of the page as we draw magnetic phenomena. And so what we're looking at here is a convention where if you're seeing an X, that is a vector, vectors like magnetic fields or electric fields or gravitational fields or forces, vectors, magnitude and a direction, that's a vector going into the page. And if you just draw one like it's a current going away from you, that's how you would draw into the page. What you want to think about here is, if you've ever done any archery, right, what you're looking at is the fletching as it's going away from you, the feathers at the back of the arrow. So these guys right here, put your eye right here and look, and you're seeing the arrow going away from you. On the other hand, these two, the dots, that would be vectors coming out of the page, coming into your eye. And so again, now you're putting your eye right there, and you're looking at the dot coming to you. So that's either maybe a magnetic field coming out of the page towards you, or current coming out of the page towards you. And so what we're trying to show here is here's current going into the page at the center, and these are those compasses that are going around in the plane of the page. And this is current going into the page. Okay, and you may be asking yourself, how do I remember if the current is going into the page, whether the magnetic field is clockwise around the wire or counterclockwise around the wire? And of course, there's a rule which will tell us that. It's called the right hand rule. And here's how it works. Up here, you can see somebody is pointing their thumb, and this is of the right hand, not the left. The mathematicians have decided that our convention will be based on right-handedness, because most people are. You put your thumb in the direction of current, and your fingers will swirl around in the direction of the magnetic field as it makes these complete loops around the wire. Okay, and so that's our first right-hand rule. You're going to look at the worksheet today, and it's going to ask you to draw something like this, only from a different perspective. It's going to move the direction of the wire and how it works. But that's how you answer the question. Put your thumb in the direction of the current. Your fingers of your right hand will swirl in the direction the magnetic field is. And your fingers will naturally curl one direction. Don't be double jointed and try to make them curl the opposite way. That's not what we're talking about here. You make your hand look just like this picture here. And of course, one of the things you might expect is that once you got the magnetic field lines drawn, we're showing magnetic field vectors here, they're just tangent to those magnetic field lines at a particular point. So that's a magnetic field right there. This one's a magnetic field right there, there. And those magnetic field vectors are tangent to the magnetic field lines that you would draw on a picture like this. And just like with electric fields, how close the lines are together is indicating how strong the magnetic field is. So you'd expect right in here where the lines are closer together, the magnetic field is stronger than out here where the magnetic field's lines are further apart, and you'd be exactly right. All right. Any questions on that before I move on? We've talked about the two ways we can create magnetic fields. They're actually kind of the same. They're both moving charges, either moving charges in wires. We'll talk more about that on Wednesday, or moving charges maybe as electrons kind of swirling around the nucleus of the atom. And I don't want to create the impression of orbits like planets. It's more of just a kind of a general swirling around, like maybe water in a bowl. As you're mixing it, it's kind of swirling. There's no defined path for any particular water molecule. That's what we're talking about, is the electrons orbit around the nucleus is the word we use, but we really mean swirl. And of course, somehow the electrons are doing the same thing, and the charge on the electron, which by the way, we have no idea how the charge is distributed on the electron, but we do know that as the electrons, we say spin, that they create a magnetic field. And it's more the magnetic field we've sensed, and we're just deducing that somehow the electron is spinning. Scientists really don't know. All right, so now we got to do some math. You knew that had to be coming, and some patterns. This is kind of an eye chart, but if you look, the first row here is kind of everything we know about gravity. Okay, Newton's universal law of gravity, how to find the weight, the force of gravity. We talked about gravitational fields, what, the second week of class, first and second week of class, I guess. I don't know that I ever made you do it. In fact, I know I didn't ever make you integrate over some mass to get a gravitational field. I don't think Professor Tech did either, but you can recognize in an advanced mechanics class like you potential physics majors might take, you might take an odd shape and figure out what the gravitational field is around it by doing this integral in exactly the same way we did for electric fields for things like sticks, and I think we did some disks and that kind of thing. In any event, Coulomb's law, the force from an electric field, okay, and an electric field from a point charge. And you can see that you would expect in this third row right here, a similar thing for magnetic fields. And, you know, if nature follows the patterns that are presented here, you might ask yourself, well, is the magnetic field radial like both the gravitational field and the electric field? That is the direction of the electric field radially outward from either the charge or the mass, like it is for electric and gravitational fields? So that's the first question you might want to know if you're looking at consistency of magnetic fields with the other fields that exist in nature. I guess the second question you might ask is, since gravity and electric fields, they decrease as 1 over r squared, do magnetic fields, and that's either B or a differential magnetic field from a small piece of moving charge, do they have a 1 over r squared dependence? And I'll, as I switch the slides here to the next one, the answer will be on radial, nope. Wouldn't it be nice? That's one of the reasons why magnetic field math is significantly harder than electric or gravitational fields. Does it have a 1 over r squared dependence? The answer is, well, thankfully, yes. Okay, as you get further away from the moving charge, there is a decrease in the magnetic field that falls off as 1 over the distance squared, just like it did for the other two. Because the math is harder, I think I have to take a little break here, just do some quick math to remind you of the ways that you can multiply vectors. Okay, and the first way, the most common way, the one people like the best, I think, is called the scalar or dot product, called the projection product. And I just want you to remember, this is how it's defined, right? The dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. So I've just drawn on a two-dimensional plane vectors A and B here, and the angle in between them, and magnitude of A would just be how long A is, the magnitude of B is how long B is. Trigonometry is what allows you to calculate those things like Pythagoras' theorem, and you can do the dot product. Okay, so in a three-dimensional coordinate system, okay, X, Y, and of course in a right-handed, key word there, right-handed coordinate system here, that's supposed to be the z-axis. It's out of the page, so if X is to the right, Y is up, Z is coming out of the page. Remember how we said we denote that? It'll look just like that, like an arrow coming right out. That's our out of the page symbol. It seems to me that following the definition of the dot product, okay, if I dot two unit vectors, I, J, and K, with themselves, the answer should be 1. Why? Because the angle between a vector and itself is 0 degrees or 0 radians. The cosine of 0 is 1, and so a unit vector has magnitude 1, hence the name. 1 times the cosine of 0 is just 1. On the other hand, I dot j, well, I and j are 90 degrees apart. Cosine of 90 degrees, that's 0. So anytime you dot a unit vector with one of the other two unit vectors, I dot j, I dot k, or j dot k, which are 90 degrees apart, because the cosine of 90 degrees is 0, well, that kind of tells you the answer for when you're dotting those two vectors. Why? Well, what if I have two vectors, A and B, looking just like that? The question, I guess, we've all found out is the dot product of A and B, you just take the x component and the x component of the two vectors, and you multiply them together, and you add that to the y components multiplied together, and you add that to the z components multiplied together. The question's why, though? Okay, why is that true? And I think it deals with what we just said. If you think about it, if I'm going to multiply A and B, that means I should get 9 terms. Think about where they come from. I have the vector A written here, here, and here, and then each of those components gets multiplied by vector B, and by vector B. And so I take the first component of vector A and I have to multiply by all 3 components of vector B, one at a time. And then I take the second component of vector A and I have to multiply it by all 3 components of vector B. And then I have to take the third component of vector A and I have to multiply it by all the components of vector B. And the distributive property applies. And so I wrote them out one at a time here, and you could count, there's 9 of them, right? A xi times bxi is right there, and I wrote it right there, and I kept doing that consistently all the way through. Now, remember, I dot I is 1, j dot j is 1, k dot k is 1. There's a k dot k, there's a j dot j, replace those with 1, and there's an I dot I as I wrote these out. And I tried to be systematic so they'd be in the same place. What you notice, though, is everything else that I haven't circled there, that's an I dot j, a j dot k, or an I dot k. It's one of those 3. So those don't exist. The only 3 that exist are ax, bx, ay, by, az, bz, and then you just add them all together because the unit vectors become 1. And so that's the result. That one's pretty straightforward. Scalar product, dot product. Multiplying 2 vectors with that method, most people are comfortable with it. I bring that up as a kind of an introduction for what we need to talk about for magnetism, unfortunately, because magnetism deals with the cross product. We're going to see here in a second. Mathematicians didn't invent the cross product. Nature invented it. Mathematicians just developed it to explain phenomena like magnetism that we see in nature. And hopefully you know that unlike the dot product, when you multiply 2 vectors via this cross product, also called a vector product, you can see in the dot product, the result was a scalar. When we do the cross product, the result is going to be a vector. All I can tell from this definition, though, is what's the magnitude of that vector going to be? And it looks very similar to the dot product. The difference, of course, is the dot product was the cosine of the angle in between them. In this case, the cross product is proportional to the sine of the angle in between them. Okay, that kind of changes things around a little bit. If you take the cross product of a unit vector with itself, okay, the sine of 0 is 0. So anytime you take the cross product of a unit vector with itself, you get 0. On the other hand, when I cross a unit vector in the x direction with one in the y direction, in a right-handed coordinate system, you get a unit vector in the k direction. And that is how the cross product is defined. This rule right here defines the direction of the cross product. This rule right here defines the magnitude. Okay, and so there's some consistency here, I guess. If you go j cross k, that gets you I back. The relationship between these directions in space is identical. You're just rotating the 3-dimensional coordinate system around. K dot I gets you j, the missing vector. Okay. On the other hand, though, if you swap the order, because the cross product isn't commutative, it does matter what order you do this in. If instead of going I dot j, you're getting k, if you go j dot I, you get minus k. And similar for the other 2 directions. Okay. And by the way, that was a convention. It didn't have to be that way. in that right-handed system that we started off with, defining which way around a current carrying wire the magnetic field swirls, we also have defined our cross product to be what we call right-handed. So again, X direction, Y direction, and Z direction are perpendicular to each other in this orientation, which causes this rule to be true. It could have been a different way, but somebody decided to be consistent and stay with this. All right, so what does that mean? If we have two vectors where we give their components in IJK notation, and I want to multiply them together using the cross product, the mnemonic that helps you remember the terms, and remember, just like dot product, there's going to start off being 9 terms. In the case of cross product, 3 of them will be 0 because of this, and the remaining 6 terms can be written out using this determinant. If you know how to evaluate a determinant, what you do is you multiply the unit vector I by the product of AY, BZ, and then you subtract off BY, AZ. And you do the same thing for J, only it's AX, BZ, BX, AZ. But of course, the J term is negative, and that's a rule for linear algebra that you may or may not have encountered. And then when you want to do the K, that's back to being positive, and it's AX, BY, and minus BX, AY. And so why is that true? Why does it work? Well, exactly the same thing we talked about for dot product. It's just a different set of what happens to the unit vectors. In exactly the same way, you have to multiply vector A's X component by all of vector B, and that's what I did right here. And then AY times all of vector B, and then AZ times all of vector B gives you 9 terms. But as we pointed out, that one, and that one go away. And then you got to watch I cross J, that becomes K, right? And then I cross K becomes minus J, and so on. And so there's the 6 terms. If you want to remember those 6 terms without having to start with the 9, cross out 3, like I did right here, you can just remember this determinant right here. And the rule is you put the unit vectors up at the top, you put the first vector on the second row, and you put the third vector on the third row. And that's cross product multiplication of vectors. And those are the rules. Now, a lot of people don't like that, and I can understand it. It's pretty mathy. But if you can remember this rule up here at the top to get the magnitude, another way to remember is this right-hand rule that is a companion to our work from Oersted and what direction a magnetic field swirls around a current carrying wire. The rule is, of course, you take your right hand, you put your fingers in the direction of the first vector, and then you swirl your fingers towards the second vector. There's only one way your right hand could do that. Your thumb just then points to the resulting vector of which is the product of the two, okay? And so I guess if you were looking at this and that was maybe the x-axis, and although not shown very well, let's make this the y-axis. Well, then I guess this must be the z-axis, and that's why I cross J is equal to K, because we've chosen to have this work like your right hand does, and you go from the first vector to the second vector, fingers on the first. I've heard people say, and then your palm points towards the second, your thumb points where the resulting product is. That's all fine too, okay? And whatever you do, some people point their index finger this way, move their middle finger to B. This can only work with your right hand. Don't do the left hand. And you can figure out what the direction of the cross product is. And of course, to get the magnitude, you take the magnitude of A times the magnitude of B times the sine of this angle that's in between them. And so that's your option. Okay, why do we care? Well, I think here's the answer. And then I'll be done and let you get started on the worksheet. I'll probably be done just a moment or two early here. The electric field we said was KQ over R squared. I remember K was Coulomb's constant, 1 over 4 pi epsilon 0. Epsilon 0 was 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. Well, there's a very similar equation for magnetism. Unfortunately, you have a cross product in it. We said magnetic fields are caused by moving charge. So in place of Q, I have a Q times a velocity. but I have to have this factor of sine of theta here. And that's a little bit tedious, but it's there. The constant here, which I call K sub m, is more frequently written this way. Okay, much like you had 1 over 4 pi epsilon 0. For magnetism, the Coulomb light constant for magnetism is a different constant in place of the permittivity of free space. We have this mu, that's a Greek m, subscripted 0 for free space, called the permeability of free space, and its magnitude is 4 pi times 10 to the minus 7th Newton per amp squared. Okay, and so that's the constant we put right there. You'll notice though, mu naught divided by 4 pi is just equal to 10 to the minus 7th Newton per amp squared. Okay, and so that's the deal. That's the constant that we put right there. We have to have QV, and then the sine of the angle. Angle to what though? That's always the question. Still over r squared like you'd expect it to be. And here's going to be the answer, where you had a radial unit vector saying that the electric field was radially outward from the charge, or radially inward, I guess, if the charge is negative. In this case, you have a cross product with the radial direction outward from the charge towards where you're calculating the magnetic field. I got to give you a picture of that. Can't talk to it without a picture. And so here it is, I guess. Let's see. Yeah, I'm gonna put the charge in a wire here, and this is a charge moving with some velocity. This is going to be for Wednesday. We'll talk about a current and a distance right here, but there is the charge moving with some velocity. Okay, the charge is sitting right here in the wire, and this is where I'm trying to find the magnetic field. There, right there, between these two vectors, that's the angle theta, okay, that we're talking about. And so right there, the angle theta that I'm talking about is the angle between the motion of the charge and the direction to where I'm trying to find the magnetic field. And so there's my picture, okay? And you can see, if I use the right-hand rule, put my right hand, and I got to kind of screw it upside down here, put my index fingers in the direction of the moving charge, in the direction of the current, swirl my fingers to where I'm trying to find the magnetic field, my thumb is pointing downward. And so that means that the magnetic field out here at the point P, well, it must be downward because of that piece of charge. And I've shown it incrementally because there's all kinds of charge in this wire, and that's what we'll be talking about on Wednesday. I'll show you a picture of this here in a second for the worksheet that you're going to do. I have to say a few words about units because we've got to do that. Let's see. A unit of magnetic field named after a guy named Tesla. I find it interesting that Newton per Coulomb or volt per meter are what we use for electric fields. When we have a similar set of parameters like that for magnetic fields, we named it after Nikolai Tesla. The symbol is T. If you look at the equation, okay, this magnetic constant has units of Newton per amp squared. The charge has units of Coulomb. A velocity has units of meters per second. And then, of course, a distance has units of meters squared. I will say this. What are the units on that guy? And it's a unit vector. Unit vectors are dimensionless. So nothing right there. What's the magnitude of that guy? 1. No units, no magnitude. All this does is tell you what direction the magnetic field is going to be for the case of a moving charge. In any event, moving back here then, I guess that guy cancels one of those. And a Coulomb per second, well, that's the same as an amp, so it cancels one of those. And I think what I'm left with is a Newton per amp. I canceled the meter in the last slide. So a Newton per amp divided by a meter, that amp can actually move down into the denominator. And so the unit of a magnetic field, which is a Tesla, is a Newton divided by an amp meter. Okay. And a Tesla is a big magnetic field, the most powerful, strong MRI machines that you can envision. In a laboratory, maybe 30 Tesla. You're not going to find 1,000 Tesla magnetic fields on Earth anyway that we can make. Okay, you can see medical MRIs are about a Tesla and a half with very, very low resistance wires, superconducting wires, where you get the current up really high, so the charges are moving really fast. You might be able to get up to 30. The Earth's magnetic field. Okay, do I have it on here? Surface of the Earth, about 0.5 times 10 to the minus fourth Tesla. Now, people hate numbers like that. So another unit that people have developed is something called a Gauss. And a Gauss is 10 to the fourth Gauss is a Tesla. And so that takes care of this 10 to the minus fourth. And so the Earth's magnetic field is about a half a Gauss. And that's just a unit people develop because it puts magnetic fields that we typically measure in a number that is, you don't have to talk about scientific notation. You can just say a half a Gauss or a full Gauss if you got twice the Earth's magnetic field. People sometimes like to talk about how the magnetic field lines are distributed over an area. And if you're thinking about electric flux, you kind of are on the right track. A Weber is a unit of magnetic flux, which is a field times an area. If you divide the area away, well, you get a Weber per meter squared, and that is also a Tesla. And so Webers, abbreviated WB, we're going to show when we find magnetic fluxes, just like we found electric fluxes, field times area. A Weber is just a magnetic field Tesla times a meter squared. And so those are the units. All right, before I let you go, I want to set up the first worksheet problem. The only worksheet problem for today. It's right-hand rule questions, and then how to calculate a magnetic field from a moving charge. And so, probably the quickest way is why don't I open it up on why don't I open up in Canvas? And so let's share screen with you again, Canvas, and let's come over to our home screen. Just those of you who haven't found the worksheets, I'm pretty sure everybody has by now. I love when it jumps around like that. And let's see, today we're talking about worksheet 24, PHY112, which will be that guy right here. And you can see the first question deals with Ørsted's work in determining what's the direction of the magnetic field here and here. And then the second, and this is, I don't think I mentioned this, the guy who came up with this, how to find the magnetic field someplace with a moving charge, actually two people, Biot and Savart. They're both French mathematician, natural philosophers in the time of Napoleon. It's not surprising you find a lot of French names from the 1800s because Napoleon invested heavily in this kind of work. And what you can see here is a charge moving along in the positive x direction with some speed, okay? And where I'm trying to find the magnetic field is right here at the origin. So this vector here is r, okay, which is what you'll square in the denominator of the magnetic field equation. And this distance right here, this angle right here, is the angle whose sign you'll take. It's the angle between Q and V and r. Now, the one thing to remember about r in the numerator, it's a unit vector, so you divide it by its own magnitude. So it doesn't even come into the calculation, but you take 10 to the minus 7th Newton per amp squared, you multiply it by the charge, you multiply it by this velocity, and then you divide through by this distance squared, and that'll let you calculate the magnitude of the magnetic field, okay? And so that's kind of part B, but now you need the direction, right? The direction comes from taking Q times V, that direction, and crossing it with r hat. R hat will be in the same direction as r, just 1 unit long. Okay, so you put your index fingers along the x direction, you swirl your fingers down to the r or r hat direction, and your thumb should be pointing into the page, and so apparently that's the direction of the magnetic field. It must be into the page. If this is the z-axis right here, because the x-axis positive is that way, the y-axis positive is that way, the z-axis is positive that way, then it seems to me that the magnitude from QV crossed with r or r hat, technically, would be into the page. And so the magnetic field at the origin is perpendicular to the plane in which the charge is moving and into the page. And I did that one for you. There'll be plenty more chances to practice this coming forward. But I think that's all I have today, unless we got any questions. All right, I'll be around for office hours at 1 o'clock this afternoon to answer any questions on either worksheet 24, which will be due on Wednesday, of course, or worksheet 23 from last Friday on the resistor capacitor circuits, which is due, I guess, end of the business day today, 5:30. So look for an invitation to a office hour session, and everybody stay safe and healthy out there, and we'll talk to you again tomorrow. Don't forget the lab, watch those videos, fill out the sheets, the lab handout, and then upload it for us. You take care now. Have a good day. Last chance for questions before I cut it off. All right. Have a good one.